This video explores the topic of zero-flux current transformers within the framework of the European project titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. A zero-flux transformer is a current measurement device designed so that, during operation, the magnetic flux in its core is constantly forced to zero through a feedback mechanism. This is done to reduce the limits in a CT due to iron losses. In practice, as shown in this picture, the primary current you want to measure passes through a toroidal core, and a secondary winding is driven by an amplifier to generate an opposing magnetic field that cancels out the original flux. Because the core is kept in this neutral state, the transformer avoids saturation and provides a highly accurate linear measurement of the primary current over a wide range. The value of the current is then read from the secondary compensation current, which is needed to maintain that zero flux condition. Keeping the magnetic flux at zero is so valuable in precision current measurement. On the right, we see the magnetization curve of the core material. The thick S-shaped region represents the core's hysteresis. When the magnetic field reverses, the flux in the material does not return to zero, but instead follows a different path. That means the core remembers some of the previous magnetization, psi, which introduces error when trying to measure current purely from the induced voltage. The line labeled B represents the ideal linear behavior we wish the core had. But in reality, the core follows curve A, showing saturation and nonlinearity. The difference between these two behaviors is the source of measurement distortions when the flux in the core is allowed to vary freely. Zero-flux current sensors solve this problem by actively canceling the magnetic flux in the core. A feedback winding, driven by an amplifier, injects a compensation current that forces the core to operate around the very small region near zero flux, where the hysteresis effect is minimized and the behavior is most linear. The measured current is then simply the compensation current itself, which is highly accurate and stable over a wide operating range. Let's dive deeper into the working principle of Hall effect sensors. When a current-carrying conductor or semiconductor plate is placed in a magnetic field that is perpendicular to the direction of current flow, a transverse electric field is induced due to the Lorentz force acting on the moving charge carriers. The moving charge carriers experience a Lorentz force, F, given by the indicated equation, where V is the drift velocity of the carrier, Q is the charge of the carrier, and B is the magnetic flux density perpendicular to the current. This force causes the electrons, or holes, to deflect toward one side of the conducting plate, leading to a charge separation. As the charges accumulate, an electric field, VH, builds up in the transverse direction, opposing further charge motion. The provided equation indicates the relationship between the electric and magnetic force at equilibrium, where RH is the Hall resistance, and S is the cross-sectional area of the conducting path. In a practical Hall effect current sensor, the magnetic field B is produced by the current-carrying conductor whose current I is to be measured. The Hall element, a thin semiconductor plate, is placed in proximity to the conductor, sensing B via the generated VH. Knowing B and material parameters, the current I can be obtained. Hall effect sensors are mainly manufactured in two categories, namely closed-loop and open-loop. In this slide, the open-loop Hall effect current sensors are illustrated, where the magnetic field generated by the current is measured directly by a Hall element, with no feedback or compensation loop. In the left image, the primary current IF flows through a conductor that passes through a magnetic core. This current creates a magnetic flux in the core's air gap. The Hall element, blue, placed in the gap senses this flux and produces a Hall voltage, VH, that is proportional to the magnetic field and therefore to the current. The IC shown is simply the bias or control current needed to operate the Hall sensor. As expected, there is no mechanism to correct or stabilize the measurement. A simpler representation can be seen in the right image, where the primary current IP generates circular magnetic field lines around the conductor. The Hall sensor is positioned at a distance r from the conductor and detects the magnetic field B. No magnetic core is used here. The measured signal depends directly on the distance and orientation. Here we see closed-loop Hall effect current sensors, where the sensor actively cancels the magnetic field rather than measuring it directly. In the left image, the primary current I generates a magnetic field in the core, just like in the open-loop case. However, here there is also a secondary winding around the core, the Hall element senses the magnetic field and feeds that information into an electronic control loop. The loop drives a secondary current IS through the windings so that the magnetic field generated by IS cancels the magnetic field produced by IF. The system adjusts IS until the net magnetic field at the Hall plate is 0. When the field is balanced, the secondary current IS is proportional to the primary current IF. Thus, the sensor output's I/O is nearly equal to IS, which is directly proportional to the measured current. The right image demonstrates the block diagram of the closed-loop category in which the Hall cell detects any residual magnetic flux, an amplifier drives a current through the compensation winding, and then the current through the measurement resistor Rm, which is IS, becomes the output signal. Finally, let's have a look at different practical implementations of the Hall effect current sensors, ranging from industrial modules to small PCB sensors. The top row demonstrates larger modules, which are designed to measure high currents, provide galvanic isolation, and are typically mounted on DIN rails, power converters, motor drivers, energy meters, etc. In this type, the element usually has a through-hole or bus bar aperture where the primary current passes. On the other hand, the bottom row demonstrates a more compact PCB Hall sensors that are often used for lower current ranges, such as in power supply monitoring, battery management systems, and embedded electronics. Finally, on the right side, the clamp meter is represented, which is a portable clamp-on current meter that uses Hall sensors in a split magnetic core. It allows non-contact current measurement in power lines and is usually used for maintenance, diagnostics, and field measurements. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.